So there was a press release put out recently titled "Mathematical Model Predicts Best Way to Build Muscle," which that's obviously a very audacious title. That's going to suck you right in. Um, and this press release and the paper underlying it generated enough interest that it actually batted for the cycle when it came to people reaching out to me on every platform that I can be reached on. People posted about this in our Facebook groups. They posted about it in the subreddit. They messaged it to me on Facebook. They emailed it to me, and they hit me up about it in my Instagram inbox. And I believe it was different people every time. So clearly there's general interest in this, and a lot of people who want my take. So I will oblige them. So anyway, like I said, the title of the press release is "Mechanical Model or Mathematical Model Predicts Best Way to Build Muscle." The study underlying it is titled "Why Exercise Builds Muscles: Titan Mechanosensing Controls Skeletal Muscle Growth Under Load." Um, and a lot of the focus on this came from one key quote from the press release. The quote was, and this is from one of the authors: "Our model offers a physiological basis for the idea that muscle growth mainly occurs at 70% of maximum load, which is the idea behind resistance training," said Terentijev. "Below that, the opening rate of titin kinase drops precipitously and precludes mechanosensitive signaling from taking place. Above that, rapid exhaustion prevents a good outcome, which our model has quantitatively predicted." So, anyway, I think the reason that this generated a lot of buzz is because you have these people doing, like, to be clear, super nerd level research, uh, seeming to validate what the bros have been saying for a long time. 70% 1RM, that's around a 12 rep max load for most exercises. And it's, something you'd probably be doing for sets of 10 if you're trying to hit failure in about 3, 4, 5 sets. Something you'd be doing for about sets of 8 if you were training with a few reps left in reserve. So like 70% 1RM is like probably the single percentage most associated with like the 8 to 12 rep range, which is the classical hypertrophy range. And so, yeah.
It's a 3 rep max for me.
Yeah, that's fair. um, do you mind if I break subject confidentiality for my
No,
thesis
go
study
for
real
it. Go
quick?
for it.
Yeah, so this motherfucker right here had the worst bench press strength endurance of anyone in my thesis study. Trux was a subject. The total number of reps completed in a single set to failure at 75% 1RM, it ranged from 6 to 15, and you were the 6.
Yep. Mr. Six.
The 6 god, as they say. um, anyway, so yeah, I think that's one of the reasons it generated so much interest. You have very, very technical research seeming to confirm what people have been saying, like, quote unquote, in the trenches for a long time. That confluence of events seems very satisfying, and so I think a lot of people were interested in that, and I think a lot of people specifically wanted my take on it because I've been saying for years now that really the hypertrophy range probably isn't as narrow as folks have been saying. On a per set basis, as long as you're getting pretty close to failure, anywhere from sets of 20, 25 reps on the light end of things to sets of probably around 5 or 6 reps on the heavy end of things, all seem to promote hypertrophy pretty much equally well on a per set basis. So anyway, since I've been saying that, I think people were interested in my take on this. And anyway, the paper did not at all find that 70% of 1RM is the ideal load for hypertrophy. But before we can get into that, it's worth some background to talk about what the paper was actually interested in looking at. So just as background, it's commonly believed, I wouldn't say even commonly believed, it's nearly universally believed that one of the main precipitators of hypertrophy signaling is something called mechanotransduction. So, mechanotransduction is basically the idea that there are proteins within or surrounding your muscle fibers that can sense an increase in force being created by or transmitted through the muscle. And then once that force is sensed, that kicks off a signaling cascade that eventually results in increases in muscle protein synthesis. So that's mechanotransduction. And that, like I said, that's almost universally believed to be either the main or one of the main initiators of hypertrophy. There's some protein somewhere or multiple proteins, multiple places within your muscles that are accomplishing mechanotransduction, and that kicks off all of the things that eventually result in muscle protein synthesis. And there are several candidate proteins that might be the main, quote unquote, main sensor for mechanotransduction. Um, and what the authors of this paper basically wanted to put forth is that there is a possible candidate for the main or being one of the main transducers that is maybe not discussed as often as it should be. So that's referred to as the kinase domain of Titan. There are other potential candidates for mechanotransduction, probably most notably focal adhesion kinase, that kind of get a lot of press in the mechanistic, like hypertrophy signaling world. And these authors are basically arguing that the kinase domain of Titan should be getting a similar amount of attention because they think that might be one of the main mechanotransducers. Um, so what they did is they generated a pretty intricate model to essentially predict, okay, what would acute and chronic responses to resistance training look like if we assume that this particular kinase is the most important site of mechanotransduction. So if we assume that this particular region on the Titan protein is your main mechanotransducer, what would that predict? And so they generated I have to give them props for this. The model they generated was ridiculous. Like they accounted for so many variables. Like when they were modeling the effects of load on like how long this particular kinase would be open and active, they even modeled like the impact, I believe, of fiber size on ribosome density within the fiber and rates of ATP usage at different levels of contraction strength. Like there was they weren't lazy with model construction. Like they accounted for just about every variable that they realistically could have. Um, but like it did still rest on a lot of assumptions. The main assumption being it's not proven that this particular Titan associated kinase is the main mechanotransducer. It was basically assuming grant us that it is. If it is, then what could we predict? Um, and so basically, the predictions they generated from this model were physiologically plausible and more or less in line with experimental outcomes. So basically, the biggest thing they were putting forth in their research is like, hey, if we assume that this is the main mechanotransducer, we can generate predictions that look pretty much like the real world. Therefore, this might be the main mechanotransducer. Therefore, more research is warranted to see if that's the case. So that's basically what they were doing. This was more or less a very elaborate hypothesis generating model to put forth theoretical evidence to suggest that this particular Titan associated kinase deserves more actual experimental research to see if it is as important as these researchers think it might be. Like that was the main point of the paper. So the big question is this evidence that 70% of 1RM is the optimal intensity for building muscle? No, it's not. Again, the main problem the authors were addressing is that there's not enough research on this particular kinase in the first place. So this paper, I would say, is basically two steps away from constituting evidence that we could use to inform training prescription. So this was basically to generate hypotheses for in vitro research or animal research. And then if they do that research and it pans out, then it'll be time for human research, and probably 3 steps away from actual uh, implementation. Because then when you get to human research, then it's going to be mechanistic work, acute work, and then maybe longitudinal work to look at further implications of this. So we're talking about a pretty long research process, potentially leading from this paper to novel and useful insights about how to program training. But that's where things stand now. It's very, very intricate, very, very cool modeling work. Uh, but if you looked at the press release and you're counting it as definitive evidence that 70% 1RM is for sure the optimal intensity to train at, we're years, potentially decades away from being able to make any sort of statement like that grounded on this research as it stands today.
Yeah. The press releases were hilarious. The headlines were like, trainers hate these scientists for exposing the real keys to muscle gain. And
Yeah,
it's just not what they were doing.
correct. Okay. Let's see. One of the other things I was going to talk about is a study that we recently posted about on Instagram. So I'm going to skip that one and just say follow Stronger by Science on Instagram. If you scroll back, probably I would say 6 posts by the time that this episode is coming out. You'll see one with a scatter plot on it that has to do with squatting and ankle mobility. Check out that post. I was basically just going to talk about the same stuff we posted, just double dipping a little bit. But anyway, I'll skip that one. So let's talk about caffeine. Caffeine's good stuff. If you're following along on video, I've got my coffee. I like caffeine. It's nice. And caffeine is also for the ladies. And that's what we're talking about here. So there was a meta-analysis that came out a couple months ago, titled "Ergogenic Effects of Acute Caffeine Intake on Muscular Endurance and Muscular Strength in Women," a meta-analysis by Gurgic and Del Coso. And this was, I would say, an important meta-analysis because we've talked about how caffeine is a useful ergogenic for increasing force output and increasing strength endurance on the podcast several times. And I think we have touched on sex differences in caffeine metabolism. But there was some degree of trepidation, certainly within my brain and also within the research community, about whether or not research on the ergogenic effects of caffeine generalized from males to females. There were a couple reasons for that. First off, a couple of the early papers looking at the potential ergogenic effects of caffeine in women failed to find significant effects, whereas similarly designed studies did find significant effects in males. So there were some early suggestions that maybe caffeine was ergogenic in males but not females. Secondly, it's known that estrogen affects caffeine metabolism. Specifically, it affects the functioning of the CYP1A2 gene, which is or the CYP1A2 enzyme, which is the rate limiting enzyme in caffeine metabolism.
It carries the load for like 95% of caffeine metabolism.
Yeah. So, and there are also some suggestions that say CYP1A2 gene variants might affect well, they certainly affect caffeine metabolism and potentially, therefore, the ergogenic effects of caffeine, although that's not quite as clear. So, maybe if there's a hormone that's affecting caffeine metabolism, that could affect the ergogenic effects differently in males versus females. And also some degree of trepidation just related to the fact that there was there was very little research looking at the potential ergogenic effects of caffeine in women. So just to illustrate, there was a 2020 meta-analysis looking at the impact of caffeine on strength and strength endurance. This was not a meta-analysis that specifically restricted. I was checking it real quick to see if you were an author on it. You were not. When was the meta on caffeine that you were a co-author on? Is that like
Uh,
2018, 2019?
Something like that. The years all blend together at
Yeah,
my
whatever.
age.
So yeah, the most recent meta-analysis looking at the general ergogenic effects of caffeine on resistance training, acute outcomes, was published in 2020. It didn't restrict the subjects to only males, but 19 studies were included, and of the 19 studies, 15 used exclusively male subjects. Two used mixed sex cohorts that were still very strongly slanted towards male subjects. So one had 11 total subjects, including 9 males and 2 females. One had 17 total subjects with 13 males and 4 females. And of the 19 studies, only 2 used exclusively female subjects. So, we're talking about theoretically a meta-analysis on the effects of caffeine independent of sex, but functionally it was a meta-analysis on the impact of caffeine in males, because males accounted for 87% of the subjects in the studies included in that meta. So even relative to exercise science generally, the caffeine research was very, very slanted towards having male subjects. There's a 2014 paper that people bring up a lot, showing that in exercise and sports science research, about 60% of the subjects are male, about 40% female. So when you're looking at 87% male subjects in a particular body of research, you're really dealing with a body of research where the potential impact of whatever you're studying on women and females is very underrepresented in the body of literature as it stands. So anyway, that was the state of the research in 2020. But since then, there's been a explosion of sorts in caffeine research in women. So in the meta-analysis I'm going to be talking about here very briefly, there were 8 studies included looking at the impacts of caffeine versus placebo on 1RM strength and measures of strength endurance. And of the 8 studies included, 5 of them were published in either 2020 or 2021. So a majority of the research looking at the effects of caffeine on resistance training outcomes in women has been published in the last year. And with that in mind, they performed a competent meta-analysis looking at the effects on 1RM strength and strength endurance, and found that caffeine has a small positive effect on 1RM strength and strength endurance in women. And the effect size estimates from this meta-analysis were virtually identical to the effect size estimates observed in the prior meta-analysis I mentioned that came out in 2020 and basically included all male subjects. So currently, at this point, it seems that caffeine is also ergogenic in women and is similarly, the ergogenic effects are pretty similar regardless of sex. So that's where the research stands currently. And I gotta, yeah, can't talk. I gotta be honest. It was nice seeing how many more studies in the area have been published in the last year, for us to be able to see a meta-analysis on it and be able to make that comparison.
Yeah, it's cool because I see Del Coso in the outline here. It was a few years back. I think his group published a paper, and the entire purpose of the paper was to bring awareness to the fact that it was like, hey, there was a huge absence of caffeine research in women. And so it looks like people saw that paper and said, yep, we got it, took that directive, and now we're starting to see some of that research finding its way into journals. And you got to understand that there's going to be a lag time there, usually of at least 1 to 2 years, but often longer when it, from the time a research idea is formed and then the study gets planned, ethics approval, recruitment, data collection, writing, rejection,
filing
rejection,
grants for
rejection.
funding.
Yeah, I mean, yeah, and it can be several years. So I think we're starting to see, some of the fruits of that labor when it comes to bringing awareness to. Why is that funny?
Well, no, I was just thinking of other times that's happened. Probably the biggest example I can think of is, and this kind of circles back to the first paper I talked about, the modeling paper from the research roundup. Uh, the low load versus moderate load hypertrophy research. There was that paper by Mitchell, I think in 2013, 2014, which was just looking at unilateral knee extensions, 80% versus 30%, finding pretty similar hypertrophy, which at the time was a pretty novel finding. And then, like you said, it takes about 2 years to get new studies out. You could have set a clock from the time that Mitchell paper was published. 2 years later, there was a deluge of like a dozen studies coming out over the span of about 18 months, largely confirming those findings. But yeah, I mean, there was a very influential paper, about a year, 2 years of lag time, and then boom, everybody starts getting in on it. Uh,
Yeah, which is exactly how it should work.
Correct. Yeah.
A lot of times you'll see people who have an idea that they're very fond of, and they'll say, "But there is evidence for this," and they'll show you one paper with like 24 participants, and you're
Mhm.
like, "Let's wait until that next wave of 8 or 10 other papers comes out and see if we can, figure out the pattern there."
Yeah. Yeah.
So it's good to see for sure. I get nervous anytime I say something, especially if it's a saying or a phrase, and you start laughing because like I I don't read and I don't consume really any type of content.
Mhm.
And so I don't know how people speak these days. I feel like I'm always like walking into some kind of linguistic trap whenever that happens. But I'm glad to see that you were just thinking of something else. Um,
No, whenever I think my knee jerk response to just about anything that happens in my brain is to giggle.
yeah, that's good.
So it's fine.